Hello students, welcome back to our chemistry class. In our today's class, we are going to discuss about the conductance of electrolytic solutions. But before we start, we shall know about the following terms. The first term is here, resistance. It is denoted by R. We all know that resistance of any conductor is the opposition offered by it to the flow of current. Its unit is ohm. Resistance of any conductor of length L and area of cross section A is directly proportional to its length and inversely proportional to area of cross section. So we can write here that resistance is proportional to L upon A, or we can write here that resistance is equal to rho L upon A. Here rho is resistivity of the conductor. Its unit is ohm meter. Reciprocal of resistance is known as conductance, which is our next term. It is denoted by G. We can define it as that it is a measure of ease by which current flows through any conductor. We can write as G is equal to 1 upon R. Its unit is Simon, written as S, or also we can write as ohm inverse or mho. Now we can see here that conductance is inversely proportional to resistance. So we can write here that G is equal to 1 upon rho A upon L, or we can write that conductance is equal to kappa A by L. Here kappa is conductivity. We can define conductivity as the reciprocal of resistivity. Now suppose area of cross section of the conductor is 1 meter square and its length is 1 meter. Then in that case we can write here then G will be equal to kappa, or we can say that conductivity of any conductor is equal to the conductance offered by a conductor of unit length and unit area of cross section. Unit of conductivity is Simon per meter, or another unit we can take it Simon per centimeter also. Now let us see the differences between electronic conductance and ionic conductance. Electrical conductance in solid conductors is known as electronic conductance. It occurs due to flow of electrons. The main factors which affect electronic conductance are the nature and structure of metal, the number of valence electrons present in it, and the temperature. Generally, electronic conductance decreases with increase in temperature. On the other hand, in any electrolyte, when it is dissolved in water, it provides ions. So there the conductance of current is due to the motion of ions. So such conductance is known as ionic conductance. The main factors affecting ionic conductance are the nature of electrolyte, whether it is strong or weak, the size of ions, the nature of solvent and its viscosity, the concentration of electrolyte, and also the temperature. Here the ionic conductance increases with increase in temperature, because on increasing temperature the ions they start moving at a faster rate. Now let us see that how can we measure the conductivity of any solution. Two main problems arises during measurement of resistance and the conductivity of ionic solution. First, passing direct current through the solution can change its composition. Secondly, it is very difficult to connect a solution into a bridge of wires. for the measurement. The first problem can be solved by using alternating current in place of DC. To resolve the second problem, specially designed conductivity cells are used. Here is a diagram of commonly used conductivity cells. A conductivity cell consists of two platinum electrodes coated with platinum black. The area of cross section of this plate is A and distance between the two plates is L. Now, the column of solution confined between the plates of the conductivity cell is considered as a column of length L and area of cross section A. So, the resistance of that column of solution can be written as resistance is equal to rho L upon A. Here, the solution whose conductivity we have to determine, that will be filled in this conductivity cell and then it will be connected to the meter bridge, and from there the value of resistance can be determined. So the quantity L upon A, this distance between the two electrodes and area of cross section of the electrode, this quantity L upon A will always remain constant for a particular conductivity cell. Whichever solution we use here, the quantity L upon A will be constant. It is known as cell constant. It is represented by G with asterisk mark. Now, we all know that resistance is equal to rho L upon A, or we can write 1 upon kappa, and in place of L upon A we can write cell constant. So we can write here that cell constant G star will be equal to conductivity into resistance, or we can say that for a particular conductivity cell, this product of conductivity and resistance will be constant. Or we can also write as K1 into R1 is equal to K2 into R2. Using this relation, we can calculate the conductivity of any solution. Now let us discuss about the molar conductivity of any solution. Molar conductivity of any solution is equal to the ratio of its conductivity and the molarity. If conductivity is in Simon per meter unit, then we can calculate molar conductivity as kappa upon C into 1000, and its unit will be Simon meter square per mole. On the other hand, if conductivity is in Simon per centimeter, then molar conductivity can be calculated as kappa into 1000 upon C, and now the unit of molar conductivity will be Simon centimeter square per mole. Now let us practice our numerical based on calculation of molar conductivity. So here is the question. Resistance of a conductivity cell filled with 0.1 molar KCl is 100 ohm. If the resistance of same cell when filled with 0.02 molar KCl is 520 ohm, calculate conductivity and molar conductivity of 0.02 molar KCl. Conductivity of 0.1 molar KCl is given here 1.29 Simon per meter. So here we see that when the conductivity cell was filled with 0.1 molar KCl, the resistance was 100 ohm, and when it was filled with 0.02 molar KCl, the resistance is 520 ohm. And we all know that for a particular conductivity cell, the product of conductivity and resistance is constant. So we can write here K1 into kappa 1 into R1 is equal to kappa 2 into R2. Let it be for 0.1 molar KCl, and this 2 mark, let it be for 0.02 molar KCl. This is an easy way to calculate it directly. Now for 0.1 molar KCl, conductivity is how much? 1.29, and its resistance 100 ohm. And for 0.02 molar KCl, conductivity we have to determine, and resistance is given here 520 ohm. So we will get here that kappa 2 will be equal to 129 upon 520, or we will get here conductivity of the solution will be equal to 0.248 Simon per meter. So in this way we have determined the conductivity of 0.02 molar KCl. Now let us calculate the molar conductivity. Molar conductivity can be written as kappa 2 upon C into 1000. Kappa 2 I am taking because we have to calculate for 0.02 molar KCl. Now we can put the values 0.248 upon 0.02 into 1000. On calculating we will get here 124 into 10 to the power minus 4 Simon meter square per mole. In this way we can calculate the conductivity and molar conductivity of any solution. You all can practice some more numericals based on this conductivity and molar conductivity. Now let us see about the variations of conductivity and molar conductivity with concentration of solution. It has been found that conductivity of any solution always decreases with dilution, because on dilution the number of ions per unit volume decreases. As a result of this, conductivity also decreases. But this is not the case with molar conductivity. We all know that molar conductivity means the conductivity of a solution containing 1 mole of electrolyte. So we can write molar conductivity in another form also. Molar conductivity lambda m can also be written as conductivity into V, where V is volume containing 1 mole of electrolyte. Now on dilution conductivity decreases, but the volume containing 1 mole of electrolyte goes on increasing, and this increase in volume compensates for the decrease in the value of conductivity. As a result of this, the molar conductivity goes on increasing with dilution. As the solution will be diluted, the molar conductivity will go on increasing. At about infinite dilution, when the concentration will approach 0, at that particular point the value of molar conductivity will be maximum. So that maximum molar conductivity at infinite dilution is known as limiting molar conductivity. It is denoted by lambda naught m. Now let us see the variation of molar conductivity with concentration for strong and weak electrolyte. The molar conductivity of strong electrolyte is weakly dependent upon the concentration. If we plot a graph between molar conductivity and the square root of concentration, then in that case the y-intercept will give us the value of limiting molar conductivity. Here the slope is known as Kohlrausch coefficient. It can be represented by an equation that molar conductivity at any concentration is equal to limiting molar conductivity minus AC to the power half. This expression is for strong electrolyte. Here the value of A depends upon the type of electrolyte. Type of electrolyte means it depends upon the charge present over cation and anion of any electrolyte. For example, any electrolyte having +1 charge over cation and -1 charge over anion will come under 1,1 type. For example, KCl, it is of 1,1 type because charge over cation is +1 and over chloride is -1. Same way, any electrolyte in which +2 charge is present over cation and -1 charge over anion, that will come under 2,1 type. Same way, calcium sulfate having +2 -2 charge comes under 2,2 type. So all the electrolytes of same type will have same value of A, that is Kohlrausch coefficient. Kohlrausch gave a law known as Kohlrausch law of independent migration of ions. According to this law, the limiting molar conductivity of any electrolyte is equal to sum of individual contribution of its cations and anions. For example, limiting molar conductivity of NaCl will be equal to sum of limiting molar conductivity of sodium ion and the limiting molar conductivity of chloride ion. So this law is known as law of independent migration of ions. Now when we talk about weak electrolyte, the degree of dissociation decreases with concentration. It is for weak electrolyte and this one was for strong electrolyte. So we see here that the variation for the weak electrolyte is not linear. So we cannot determine the value of limiting molar conductivity by just extrapolating the graph to zero concentration. At infinite dilution, the electrolyte dissociates completely, but then also the conductivity is very low. So to determine the limiting molar conductivity of any weak electrolyte, we have to apply Kohlrausch law. The degree of dissociation of any weak electrolyte can be determined by ratio of molar conductivity to the limiting molar conductivity. Also we can calculate dissociation constant by using formula K is equal to C alpha square upon 1 minus alpha. Alpha we can determine from here. Now let us see a numerical based on calculation of degree of dissociation and some limiting molar conductivity. Now here is the question. Calculate limiting molar conductivity of acetic acid if limiting molar conductivity of HCl is 426, for NaCl it is 126 and for sodium acetate it is 91 Simon centimeter square per mole. So here we will see that according to Kohlrausch law, limiting molar conductivity of HCl can be written as limiting molar conductivity of hydrogen ion plus limiting molar conductivity of chloride ion, which is given here 426. Same way, limiting molar conductivity of NaCl can be written as limiting molar conductivity of sodium ion plus limiting molar conductivity of chloride ion, that's given 126, and limiting molar conductivity of acetic acid sodium acetate can be written as limiting molar conductivity of acetate ion plus limiting molar conductivity of sodium ion, which is given here 91. Now we need to calculate limiting molar conductivity of acetic acid. For acetic acid, we need limiting molar conductivity of two ions, acetate ion and hydrogen ion. Acetate ions we will get from this, let us number this equation. Acetate ion we will get from equation number 3rd and hydrogen ions we will get from equation number 1st. So we will add these two equations. But when we will add these two together with that, this sodium ion and chloride ion will also get added. So we need to subtract the values from equation number 2, which is for NaCl. So we can directly write here that limiting molar conductivity of acetic acid is equal to limiting molar conductivity of HCl plus limiting molar conductivity of sodium acetate minus limiting molar conductivity of NaCl. It's very simple way. Now we will put the values. For HCl it is 426, for acetic acid it is 91, minus for NaCl it is 126. So on solving we will get here 391 Simon centimeter square per mole. So in this way we can easily calculate limiting molar conductivity of any weak electrolyte. Now let us see one more example. Now here is another question. Conductivity of 0.001 molar acetic acid is 4.95 into 10 to the power minus 5 Siemens per centimeter. We have to calculate its molar conductivity and degree of dissociation. Limiting molar conductivity for hydrogen ion is 349.6 and for acetate ion is 40.9. So now let us start. First we can calculate molar conductivity of acetic acid. Molar conductivity of acetic acid can be written as conductivity into 1000 divided by C. Since conductivity is given in Siemens per centimeter, so we are using this formula. Here conductivity is given 4.95 into 10 to the power minus 5 into 1000 divided by molarity. Molarity is 0.001. That can be written as 10 to the power minus 3. So on solving we will get here 49.5 Siemens centimeter square per mole. So this we have calculated its molar conductivity. Now limiting molar conductivity. Limiting molar conductivity we can calculate using Kohlrausch law. It can be written as limiting molar conductivity of hydrogen ion plus limiting molar conductivity of acetate ion. The values are already given here. That is 349.6 plus 40.9. So that will be equal to 390.5 Siemens centimeter square per mole. Now as we have got molar conductivity and this limiting molar conductivity, so we can calculate degree of dissociation alpha as ratio of molar conductivity and limiting molar conductivity. That will be equal to 49.5 upon 390.5, which will be equal to 0.127. So in this way we can calculate this degree of dissociation. So hope everything is clear till this topic. In our next class we will discuss about electrolytic cell. So you all can practice some more numericals related to these all topics. See you in next class. Thank you.